Hi, I'm Ryan Fortenberry. I'm currently an assistant professor here at Georgia Southern, and I do work in physical chemistry. So I've been all over the place. I was originally a mathematics major, and then I got a master's degree in communication, followed by a PhD finally in chemistry. Then I did my postdoc at the NASA Ames Research Center in Mountain View, California. My research is largely centered in theoretical astrochemistry. So astrochemistry is simply put the study of molecules in space. And here we have one of the most beautiful images of an object that we have in space, the Horsehead Nebula. The object itself is made up of various different gas particles, mostly hydrogen, as well as carbon monoxide, oxygen molecules, nitrogen, and various other things. But there are also polycyclic aromatic hydrocarbons here in the Horsehead Nebula. In this near-infrared emission image taken by the Hubble Space Telescope, the image that you see here is actually made up by the emission of these large carbonaceous aromatic structures. At least we think it is. Some of the work that I am doing here at Georgia Southern, as well as in collaboration with individuals in the Netherlands, at NASA, and at the University of St. Thomas in St. Paul, Minnesota. We are trying to figure out what the infrared emission features are, what the vibrational transitions are for medium to large size polycyclic aromatic hydrocarbons. One of the ways that we're doing that is by using computers with quantum chemical programs to simulate how those atoms will vibrate inside of these molecules. I am doing the work using high-level quantum chemistry tools in order to predict these types of transitions for small molecules. Then we're going to use that set to scale up and get a larger type of calculation with a bit more approximations based on the calculations that we have done in order to see if we can predict these vibrational spectra. This project is currently being funded by NASA and will continue through 2021 as far as we know. Additionally, another project that we're working on is looking at molecules that will ultimately lead to the creation of small dust grains, and those dust grains can then aggregate into asteroids, and the asteroids can create planets. The Earth itself is made up of various different minerals. One of the most important is called magnesite, comprised of magnesium and oxygen and various other things, including sulfur and silicon. Now, if you take a derivative of that, which is periclase, it's mostly magnesium and oxygen. So the question that we have is, when do you go from a molecule and when do you create a mineral? So one of the research projects that we're working on right now is predicting the vibrational spectra of small magnesium molecules that will ultimately lead to the creation of larger minerals in order to see if we can find where in these baby stars new planets are being formed. My research is somewhat varied in that I am a chemist, trained classically as such, but I also have a large interest, as you can tell, in astronomy, astrophysics, and planetary science. But we also do research using computational methods. Hence, we're very interdisciplinary across many of the standard chemical, astrophysical, mathematical, and computer science disciplines. The research that we do is continuing to look for new molecules in space to give us a better understanding as to how life forms, to give us a better understanding as to how molecules evolve, and where ultimately we may be able to search for habitable exoplanets, as well as places where we might find life in the future. Computational astrochemistry, that's what I do.